Okay, now we are live on YouTube.
So, welcome to the One World Probability Seminar. Today we are very happy to hear Justin Salez. He's a professor at the University of Paris Dauphine. He studied in the University of Paris, also appeared at Marie Curie. Later he went for a postdoc in Berkeley and, well, some other positions afterwards. He has a background in computer science, and perhaps this explains his very creative approach to some probabilistic problems. He has very important recent work, and today we're really happy to hear two talks based on this. Thank you very much for being here, Justin.
Thank you for the introduction, and thank you for the invitation also. It's a pleasure to give this online talk. So it will consist of two parts. The first one will be completely elementary. It will be an introduction to this cutoff phenomenon. So if you are already an expert on that, you will really not learn anything new. And I recommend that you just disconnect and come back for the second part, where I will present my recent progress on this question. Okay, so let me start with the setup. So the setup that I have in mind is the following. I'm going to consider just a Markov chain on a finite state space. So the typical picture that you should have in mind is the following. Right. This is the diagram of a Markov chain on 3 states. In general, my state space will always denoted by X. Right? State space. It will be finite, but think of it as being large. And on that state space, I'm going to consider a transition matrix K, which I will always assume to be irreducible. Right. So this defines the dynamic in the usual way, but I'm going to actually work in continuous time for convenience. So the way I'm going to do that is just suppose that you have a Poisson clock that rings with intensity 1, and whenever it rings, I just make a transition according to K. Right. So the probability to be at a state Y if you start from a state X after time T. It's just given by this formula here. So you look at the sum of all possible numbers for the number of clock rings, and then you get a Poisson distribution for this number. And then given that you got n clock rings, you just apply your transition matrix n times. Right? So that's the heat kernel of my Markov chain. So any continuous time Markov chain can be put into this form, provided you rescale time so that there is only one move per unit of time on average. And because of my assumption on the state space, this probability distribution will converge as t tends to infinity to the unique invariant measure of the system. Is just the unique solution to this equation. Now you should think of this Markov chain as being, say, simple random walk on your favorite complex network, or a large interacting particle system, for example, or a Gibbs sampler for simulating your favorite high-dimensional discrete distribution. And in all those applications, you really want to understand the speed at which this convergence to the equilibrium measure occurs. And so that's the question that I'm going to address here. So how fast? Right, so if you want to answer this question, you first need to agree on a way to measure the distance to equilibrium. Right? You have two probability distribution on a finite state space, so there are many options for measuring the distance, but I'm going to focus on the one which is relevant here, which is total variation distance, and the so-called worst case total variation distance to equilibrium. So it's defined like that. You take a maximum over all initial states, and then you take a maximum over all events in your state space, and then you compare the probability to be in that event after time t versus the stationary probability. And that's the main quantity you like to understand. Okay, so let me show you a typical plot of this function. Here is how it looks. Right, so as you can see on this picture, this total variation distance is always decreasing with time. It starts very close to 1 and it goes to 0. Right? It has a very nice property, which is a submultiplicativity. Right? So the value at time t plus s is at most the value at time t multiplied by the value at time s, and you just lose a factor 2, which is not too important here. Right? And so this roughly tells you that the convergence to equilibrium occurs in in a geometric or exponential way. Right? Particularly, if you take the log of this, you get a subadditive sequence, and so you know that 1 over t times the log will converge. And because of our assumptions, it actually converges to a strictly negative quantity, which you can relate to the eigenvalues of the transition matrix. It's minus the spectral gap of the transition matrix. Okay, so this tells you that the time scale on which you should look at this graph here is roughly 1 over this rate. And this is a natural quantity that is called the relaxation time. It's 1 over the gap. Right. And on this picture, time is here, and if the distance is there, this approximation here tells you that total variation distance roughly looks like an exponential on the time scale T-rep. Okay, so it seems like this actually answers completely our question, how fast, right? Because it tells you everything about convergence, but keep in mind that this approximation is only valid when T is very large. Right? This is only valid for T large. Right, so in particular, T is so large that the distance to equilibrium here is already very close to 0. Right? So this approximation only describes what happens roughly here. It tells you that on this region of the graph, the correct time scale is here. But it does not really tell you anything about the true question, which is, how long do you have to wait before the Markov chain is sufficiently mixed so that this regime becomes valid. Right? And so this is a completely different quantity, which is usually much larger than the relaxation time. And this is called the mixing time. Right? So the formal definition of this mixing time is the following. So you have a parameter epsilon, which I will come back to later. And then you look at the first time at which your distance to equilibrium reaches the value epsilon. Right? So epsilon is any fixed parameter between 0 and 1. You should think of it as being, say, 1/10. But if you are not happy with this 1/10 precision, right, this depends on your particular application, then you can take something smaller, and the only thing that will change is that you will have a prefactor, a different prefactor in front of the mixing time. Right? Because of this submultiplicativity property, all those mixing times are equivalent up to constant factor. Okay, so this mixing time is really the fundamental parameter when you want to understand convergence to equilibrium. And there are now thousands of methods to estimate mixing times from above and from below, using information on your chain, for example, the geometry of the state space, or the eigenvalues and eigenvectors of the transition matrix, or certain functional inequalities for the corresponding directed forms. All of this is now very well developed and very well understood. Right? So if your chain is simple enough, then you can hope that your upper and lower bounds will agree up to prefactors, and then you can claim that you know the order of magnitude of the mixing time of the Markov chain. Right? So let me actually do this for you on a very simple example where you can compute everything, just to see how things work. Okay, and my example will be, my first example will be just simple random walk on the n cycle. Okay. So here is the picture. You have a cycle, discrete cycle, that, and then on this cycle you have points. So this is 0, then 1, 2, etc., and then up all the way to n minus 1. And when you are in a state x, say, and the clock rings, what you do is you move clockwise 1 unit, right, to x plus 1, or counterclockwise by 1 unit, each with probability 1 out. Yeah, so that's your Markov chain. It's a very simple Markov chain. The state space is a set of integers mod n, and then the transition matrix is simply 1 half if y is x plus or minus 1, and it's 0 over x. Right. So how long does such a chain take to mix? Think of n as being very large. So by symmetry here, the initial condition can always be chosen to be 0 without loss of generality. And then you have a very precise representation of your Markov chain at any time t. Right? You just count the number of times that you got a clockwise move, and this is just Poisson with parameter t over 2. And then you subtract the number of anti-clockwise move, which is again Poisson with parameter t over 2, independent of the first one, and you take all of that mod n. Right? So it's completely explicit. Right? And now if you think of time as being large, then you can apply the central limit theorem. This quantity here is roughly square root of t times the standard ocean. Right? So if you want this to be visible on the state space, it should be of order n, right? And it tells you that the time you should look at is n squared. So more formally, the CLT tells you that the probability that on the time scale n square, your Markov chain is inside any macroscopic set, say NU and V, any macroscopic interval, is roughly given by the integral from B to V of this function here, where the function is just the density of this random variable mod 1. Mod 1. Okay, so this tells you everything you want to know about the probability of being in a macroscopic interval. But remember that in the total variation distance, there is a maximum over all possible subsets and not just macroscopic intervals. So you need something much finer if you want to deduce something about the total variation distance. Right? Fortunately, in this example, things are so simple that you do have stronger principles. In fact, there is a local CLT here, which tells you that the probability to be precisely at any point right, on your state space, so probability that the position is precisely integer part of nz, say, this behaves as n tends to infinity, like 1 over n times the density around the point z. Right? And this is much more precise than that. Right? If you integrate this over the interval, you do get that, but you can also integrate this over any set to get the probability to find your random root in that set. Right? So this is precise enough to tell you everything about the total variation distance. Now it's just a matter of doing a computation, but we'll find that the total variation distance to equilibrium on the time scale n squared, if you send n to infinity, will just converge to a very explicit function, which is the following. So it's 1/2 integral from 0 to 1. And you are just comparing this density to the uniform density on the cycle. D. Right? So the precise formula for this function does not matter. You can express it in terms of Jacobi function, but I don't really care about that here. The main interesting point is that this function here is smooth. Right? It's smoothly decaying from 1 to 0. So this means that if you look at the time scale n square, you do see convergence in a very gradual way. In terms of mixing time, you can translate this result as follows. The mixing time of your system, given any precision epsilon, is roughly n squared. And if you want to know the precise refactor in front of n squared, well, you just have to take the inverse of this limiting function, evaluate it at epsilon. So that tells you everything about how long does it take for this random root to mix. Okay, so this was a very simple example. Let me now move to a slightly more interesting one. Still a simple random walk, but now on the n cube. Simple random walk on the n-dimensional hypercube. Right, so let me first show you a small picture for n equals 3. This is the hypercube in dimension 3. Right, in general, it's defined as follows. So your state space will be just the set of all binary words of length n. And then whenever your clock rings, what you do is you choose a coordinate uniformly at random and you flip it. If it was a 0, you turn it into a 1. If it was a 1, you turn it into a 0. Right? So transition matrix is just 1 over m. If x and y differ at exactly 1 coordinate, and it's 0 otherwise. Okay, and again, the same question, if n is large, how long should you run your random walk so that it has forgotten the initial condition? So by symmetry of this graph here, you can always choose the initial condition to be 0, as we did before, right? So x0 will be the 0 vector. And if you do that, then you have a very simple description of the position of your chain at any time t. Right? You will just have n coordinates, which are IID, and they are just Bernoulli. It's a parameter that tends to 1 half. Right? It's 1 minus t over n. Right. So as t tends to infinity, this Bernoulli parameter tends to 1 half, and so this vector here converges in distribution to a uniformly chosen state in the state space. And if you want to understand how far you are from equilibrium, you just need to compare in total variation two product measures. It's a very simple thing to do. You can estimate it very easily, and you find the following thing: that the distance to equilibrium, if you want to see something, you need to rescale time by a factor which is n log n here. And this n log n comes from roughly the coupon collector problem. Right? You'd like to have a chance to hit every coordinate, and this will take you a time over the n log n. And now on this time scale, again, you do have convergence as n tends to infinity to a function, but now the function is not smooth at all. The function is 1 if t is less than 1/4, and it's 0 if t is more than 1/4. So you do see a phase transition in the way your Markov chain converges to equilibrium. There is a phase transition from being completely out of equilibrium. Right? Total variation distance 1 really means that your Markov chain lives on a region of the state space which has 0 probability measure, essentially, under the stationary measure. And you move suddenly from 1 to 0 as soon as your time t crosses this very particular threshold, which is 1/4 n log n. Right? Okay, so let me just translate this in terms of mixing time, right? Equivalently. You can say that the time it takes for your Markov chain to reach a given precision epsilon will be roughly n log n. And in fact, the prefactor in front is now 1/4, regardless of the precision epsilon that you choose. For every epsilon between 0 and 1. So the precision is asymptotically irrelevant for mixing. And so that's what is called a cutoff phenomenon. So we've seen one example where there is no cutoff, the convergence to equilibrium is gradual, and another one where there is a cutoff, so there is a phase transition. Now, if your favorite Markov chain does exhibit such a phenomenon, in practice, you really want to know this, because you don't want to stop just before the transition to equilibrium. Okay, so let me now define the cutoff more formally, now that you've understood those examples. The name cutoff was actually coined by Aldous and Diaconis in the 80s. First occurrence is in a paper in 86, I believe. Right, so it's defined for a general sequence of Markov chain. As you have seen in examples, we're interested in mixing times when the size of the state space tends to infinity. Right? So in order to model that, you need to think of not just one single Markov chain, but a sequence of Markov chain indexed by n, and you send n to infinity. Right? So the definition of a cutoff is as follows. So your sequence of Markov chain defined on larger and larger state space, and you say that it exhibits cutoff if the mixing time is asymptotically independent of the precision, right? As was the case in our second example. Right? So the time it takes for your Markov chain indexed by n to reach precision epsilon is the same as the time it takes to reach precision epsilon prime in the infinite volume limit, right? For any fixed epsilon prime. Right? So that's the definition. Okay. But really the picture that you should have in mind is the following one. Those two mixing times, T mix epsilon and T mix epsilon prime, are here. And when this ratio here tends to 1, it really means that this graph approaches a step function. So in the limit, you do have a phase transition for the convergence to equilibrium of the chain. Right? So some sequences of Markov chains do satisfy this phenomenon, some others do not, and we'd like to understand why. Okay. So let me now give you a brief history of this phenomenon. There are now hundreds of papers proving cutoff phenomena, so I cannot give you all references, but I will just give you 5 pointers to different examples that belong to a very different context so that you can see a bit of everything. But again, it's really not exhaustive and very far from being exhaustive. Right, so the phenomenon was actually discovered in the context of card shuffling. You have a deck of n cards, and you do some transformation, some random transformation to it, and you want to know how many times you should repeat that in order for your deck to be mixed. And that's where the first occurrences of cutoff were found. Actually by Aldous and Diaconis. So this was again in the 80s. Right? Now, card shuffling, you can model that by random walk on permutations. And so these card shuffling schemes are in fact a special case of random walks on finite groups, which is a very rich source of Markov chains that do exhibit cutoff in many examples. So the nice thing when working with random walks on groups is that if your group is nice enough, if you have a good representation theory for it, then you can hope to understand the eigenvalues and the eigenvectors of your random walk, and this will help you making explicit computations. So there is a whole book on the subject, which I recommend by Diaconis. I think it was 89 or something. Okay. Another rich class of Markov chain where cutoff have been observed is interacting particle systems. So take your favorite model of interacting particles and look at the regime where the size, the number of particles and the size of the lattice that you consider tend to infinity. And if the dynamics is fast enough, there should be a cutoff in this model. And this is very delicate to prove, but it has been done in quite a few models. Maybe the best pointer that I can think of is this seminal work by Hubert Lacoin that proves cutoff for the simple exclusion process, right, on a segment. But again, I mean, this is just one pointer. If you want to have a better picture of the domain, you should just look at all the papers that cited this one, and you get a pretty decent view of this. Also, another class of Markov chains where cutoff has been observed is MCMC algorithm, and more specifically Gibbs sampling, or Glauber dynamics, if you prefer Gibbs sampling. Right, so take a high-dimensional discrete distribution and look at the natural Glauber dynamics for sampling from that distribution. If your distribution is nice enough, you may expect a cutoff, and this has been proved in certain cases. The most famous example I have in mind is a paper by Lubetsky and Salez, who proved cutoff for the Glauber dynamics of the Ising model. But again, I mean, the method that he developed applies to other examples as well, and there has been a lot of progress in this direction recently. So we'll have to look up the references there. And finally, another very rich class of Markov chain where you can find cutoff is random walks on sparse random graphs. Okay. So take your favorite model of a sparse random graph, consider simple random walk on it or non-backtracking random walk on it. Does it exhibit cutoff with high probability as the size of your graph tends to infinity? So this has been actually shown in many models. So it all started with a paper of Lubetsky and Salez for random regular graphs, but then the method was extended to apply to much more sophisticated models. And a good pointer here is a very recent work that I like a lot by Hermon, Salez, and Suzy, that proves cutoff for graphs that are obtained by adding a random perfect matching to a fixed deterministic graph. Right, so this is one of the very recent works on the subject, but if you look at the references there, you will see many other works that prove cutoff for sparse random graph. Okay, so I hope that from this list you get a feeling of the ubiquity of this phenomenon. Right, it's still a list that grows every day. Right, it's expected. The phenomenon is expected to be universal, in fact, at least among high-dimensional systems, fast mixing systems, say. But we are very far from having a proof of that. In fact, all the papers that are listed here work with arguments that are extremely model specific. So far, the only method to prove a cutoff is to actually analyze your model so well that you manage to get a very precise description of the distribution at any time t, so that you can make almost explicit computations of the total variation distance to equilibrium and check that indeed you do converge to a step function. So it does not really tell you anything about why this phase transition occurs. And in this sense, there is really no general theory of the cutoff phenomenon. Okay, so to give you a better picture, a clearer picture of this, the difficulty of proving cutoff, I'd like to quote a few lines from the masters of the field. Aldous and Diaconis, quotes from the masters. The quote dates to the 80s or 90s, but I believe that they are still very accurate today. So I selected only 3 of them, but it's a very pleasant reading to go to these seminal works and see all the insights that was already there. So the first quote that I would like to give is the following one. So at present writing, proof of a cutoff is a difficult, delicate affair requiring detailed knowledge of the chain, such as all eigenvalues and eigenvectors. So most of the examples where this can be pushed through arise from random walk on groups, with the walk having a fair amount of symmetry. Yeah. Of course, the second part of the paragraph is a bit less true nowadays, right? We manage, as you have seen from the list, we manage to go beyond random walk on groups, but still, I mean, proving a cutoff requires a very detailed knowledge of the chain. This remains completely true. Let me give you a second quote. So the careful work required to prove a cutoff often leads to a more or less complete understanding of the chain, such that essentially any natural question can be answered. Right? So really proving a cutoff means analyzing your Markov chain so deeply that you essentially understand the distribution at any time in a very, very precise way. So of course, this is restricted to only a limited number of Markov chains. And finally, the last quote is the following. So the cutoff phenomenon occurs in all the examples which we can explicitly calculate, but we know no general result which says that the phenomenon must happen for all reasonable shuffling methods, right? And to me, this is really the most interesting point, right? We have collected a lot of examples of Markov chains that do exhibit cutoff, but there is still no rigorous explanation as to why this phenomenon occurs so ubiquitously. Okay, so let me now give you the precise question that I would like to advertise. Right? So to me, it's really the main challenge in this field. And again, the question was already present in the seminal works by Aldous and Diaconis. And it is as follows. So let me summarize it. Right? The question is, can we find effective criteria which allow us to predict a cutoff without having to really analyze the model in detail, so without having to explicitly compute the mixing time, the limits of epsilon, within a precision 1 plus little of 1. And this, to the best of my knowledge, is still widely open. So what can we expect? So let me just give you a very rough analogy with concentration of measure. If you think of a real valued random variable, saying that it's concentrated around its median, say, is the same as saying that the cumulative distribution function of this random variable looks like a step function. Right? And as you know, there is a very rich theory that allows you to predict that this will be the case without having to know anything specific about the distribution of your random variable. You have a lot of general ingredients that allow you to predict concentration. Right? You don't even need to know the value of the mean in order to conclude that the random variable is concentrated around the mean. Right? So this is the sort of thing that we would like here, but for the cutoff phenomenon. And for those of you who know also, there is another very vague analogy to the theory of sharp threshold for monotone Boolean functions. Right? So think of percolation, for example. So there have been tremendous progress in the past years to develop tools that now allow you to predict that monotone function will exhibit a phase transition as the probability parameter reaches a certain threshold. And you know that the transition will be sharp without having to know the explicit value of the critical threshold. Right? So that's the type of results that we would like to have, but for the cutoff phenomenon for Markov chain. So this is only a very rough analogy, and the problem for Markov chain is completely open. Right? And this is true despite having accumulated 40 years of examples of cutoff. Right? And it's even worse than that. It's completely open even if we restrict attention to very simple chains. To simple chains. And I would like to give you a few interesting classes of chains for which we would really like to know, to understand cutoff, but which so far is still very far from any concrete result. Okay, so of course, one obvious simple class of chain is a reversible chain. I'd like to assume that the chain is reversible, for example. So this means that it satisfies the detailed balance condition. And this is equivalent to saying that the transition matrix is self-adjoint in the appropriate Hilbert space. Right? So if you have that, then you know that you can diagonalize your matrix. You can find an orthonormal basis of eigenvectors, and therefore you can have very nice expressions for the large powers of your matrix K, and this should give you a very good control of the distribution at time t of your system. So it's reasonable to hope that this will help you in understanding the cutoff phenomenon, but so far there is no general result in this case. So let me be more specific and
there is a question in the chat.
Yes.
It's saying, can cutoff be conceived just as a form of phase transition? Is there a specific relation between the two?
Yes, so it is a phase transition for the it's a phase transition for the distance to equilibrium. Right? The distance to equilibrium remains close to 1 for a very long time, and then suddenly, as time passes a certain threshold, the distance drops to 0. So that's exactly a phase transition. Now, beyond that, there is no, the analogy that I gave with concentration of measure or Boolean functions, there is nothing more precise than that. It's just, in all those cases, it's about a function that becomes a step function in the limit. That's what I meant. Okay, so a very specific class of reversible Markov chains, which is interesting for applications, is of course simple random walks on graph. We'd like to understand, to have criteria that are based on the geometry of graphs to predict that they will or they won't be any cutoff, but we still have nothing in that direction. Now, let's be even more specific. Instead of looking at all graphs, you could look at graphs that have a lot of symmetry, for example, vertex-sensitive graphs, or even more restrictively, you could look at simple random walk on a Cayley graph of groups. Right? So, Cayley graph, remember, Cayley graph is something like that, where this is a group, and this here is a subset of your group. And the graph is as follows. So the vertex set is just your group itself, and the edges are all the pairs that you can form by taking an element of your group and multiplying it by an element from the set S. Right? So again, those graphs are very structured, very symmetric, and so we understood a lot about their geometry. And so it's very natural to wonder if the cutoff phenomenon can at least be understood on those graphs. But again, there is no known characterization even on Cayley graphs. So let's be even more restrictive, and let's assume that the group is extremely simple, that it's abelian, right? So roughly a product of tori. Right? So simple random walk on abelian graph, and still. There is no criterion here that allows you to predict that there will be a cutoff or that there won't be a cutoff, even in those extremely simple chains. Let me note that simple random walk on abelian Cayley graph, in order to know the position of your random walk at time t, what you only need to know is the number of times that each generator has been used. Right? So it should be very simple in principle to understand the distribution of such an object. And still, the cutoff phenomenon is not understood at all. Right? And let me also mention that the two examples that we have seen before, so simple random walk on the n cycle and simple random walk on the n cube, are both examples of abelian Cayley graph. Right? So those examples are more and more restrictive, right? And even for this very small category here, the answer is not known. Okay. Now, on the positive side, so let me please present you, and this will be my last slide for the first part, just one famous attempt of having a general criteria for cutoff 2 decades ago by Yuval Perez. So it's called the product condition. It will be important for the second part to understand this. So let me spend a bit of time on that. So This started with a conjecture of Yuval Perez 2 decades ago, and the conjecture is as follows. So Yuval proposed a very simple criterion to determine whether a chain exhibits cutoff or not. So it was at least for reversible chains, say, or at least for reversible chains. He proposed that cutoff is equivalent to the so-called product condition, which is a criterion that is very easy to check in practice, right? And the criterion is as follows. So you know that the mixing time of your Markov chain, which remember is indexed by n and n tends to infinity, should be much larger than the relaxation time of your Markov chain. Right? So this criterion makes a lot of sense if you remember the interpretation. Right? Relaxation time is the time it takes to come back to equilibrium when you are already very close to it. Right? And the mixing time is the time it takes to enter the regime where you become close to equilibrium. Right? So if you want your transition to be sharp, you want this relaxation time to be much smaller than the mixing time. It makes a lot of sense to require that. It's called the product condition, even though there is no product in this formula. But remember that the relaxation time is defined as 1 over the spectral gap. So if you write it in terms of spectral gap, you will see a product in this equation. Okay, so let me give you a few comments on this condition. So the first obvious comment is that it's a very effective criterion. In the sense that in order to determine whether this criterion holds or not, you don't need to do a deep and model-specific analysis of your Markov chain. Right? You don't need to determine the mixing time within precision 1 plus little rho of 1. The only thing you need to do is to find a very rough lower bound, and lower bound are much easier than upper bound, on the mixing time, and a very rough upper bound on the relaxation time. Right? It's about order of magnitudes only. The prefactors do not matter, so it's very effective. In practice, you can check that this holds in many, many examples of Markov chain. So it would be very nice if this conjecture were true. Okay. The second comment that I would like to make is that, at least on the 2 examples I presented, the conjecture seems correct. We have seen this simple random walk on the cycle, and for the cycle, you can check that the relaxation time is of order n square, which is the same as the mixing time. And therefore, according to this condition, there should not be any cutoff. And on the other hand, for the hypercube, the relaxation time, it's a product chain, so it's very easy to diagonalize it. And the relaxation time is actually equal to n. And as we have seen, this is much smaller than the mixing time, which is n log n. Right? So at least on this example, it seems to give the correct answer. Right? So one good news is that part of the conjecture is true, half of it is true. So the implication in this direction here, always true. Actually, you don't even need reversibility. It's true for any sequence of Markov chains that if you want to have a cutoff, then you should really have this. And the proof is not complicated. It really comes from this submultiplicativity property of the distance to equilibrium. And this submultiplicativity property tells you that the mixing time is always at least the relaxation time with this precise factor in front. Right? And so now if you want your Markov chain to exhibit cutoff, then you are saying that this mixing time here should not be depending on epsilon asymptotically, but this term here depends a lot on epsilon, right? So if you want this to be possible, you need this inequality to be very loose. And that's precisely what the product condition tells you. So this is a general fact. Unfortunately, there exist counterexamples to the converse. To the converse implication, and not that the converse implication is the really interesting one. Right? In practice, you would like to predict the occurrence of a cutoff. You would like to be able to justify the fact that it's supposed to be a universal phenomenon, right? But in order to deduce cutoff proving the product condition is not enough. Right? They are counterexamples. So you might think that those counterexamples are extremely pathological, but it's not the case. In fact, there are counterexamples everywhere. So let me explain that in a minute. So in fact, there is a very simple perturbation. Right? Start with your favorite sequence of Markov chain that does satisfy a cutoff, and then you perturb it as follows. You do a rank 1 perturbation. It's a very simple way to modify your Markov chain. Right? You replace your transition matrix K by this new transition matrix K tilde, which is just with probability 1 minus epsilon. You use the original transition matrix, but then with probability epsilon, you move directly to equilibrium. Right? And you should think of this epsilon as being extremely small, right? Tending to 0 with the size of the system. Now, if you choose this epsilon carefully enough, you will manage to preserve the product condition. So remember that you started with a sequence that does satisfy cutoff. So in particular, it does satisfy the product condition. Now, the modified sequence still satisfies the product condition. So this perturbation preserves the product condition, but it completely destroys the cutoff phenomenon. Right? Again, if you choose your epsilon carefully. So this tells you a lot of things, right? So first of all, it tells you that close to any nice Markov chain, there is a counterexample to the conjecture of Duval. Right? But also, if you look at this perturbation here, it's a perturbation that preserves a lot of structure of the original chain. Right? In particular, if K is the transition matrix of a random walk on a group, then K tilde is also the transition matrix of a random walk on the very same group. And therefore, you can construct counterexamples to the conjecture of Duval, even in the very structured setting of random walk on abelian groups, for example. Right? The other thing that this tells you is that this original sequence satisfies cutoff, the new sequence K tilde does not, but still those two matrices are extremely close one to the other, not only in an entry-wise sense, right? Remember that epsilon is very small, but also in terms of eigenvalues and eigenvectors. The eigenvectors of K tildes are exactly the same as those of K, and the eigenvalues are related one to the other by just a trivial linear transformation. Right? So K tilde is very close to K, but K satisfies a cutoff and K tilde does not. So it really tells you that cutoff is something that is very, very sensitive and that it cannot be captured by a condition that is too insensitive, like this product condition. Right? So if you want to find a good criterion to predict cutoff, this criterion will have to distinguish between those two models. And if you think about this, there is one aspect in which those two matrices are very different one from the other, and this is sparsity. Right? You may think of K as being extremely sparse, not many, I mean, most of the entries are 0, so think of simple random walk on an expander, for example. Right? K tilde will be very close to K, but now K tilde, all the entries of K tilde are strictly positive because of this term. Right? So the chain K tilde is not sparse at all. So somehow this suggests that sparsity should enter the product condition if you want to have something that is able to distinguish between those two models. And we'll come back to that in the second part of the talk. Still, the general belief from the community is that the conjecture of Duval is morally correct. Right? So in the sense that it's expected to hold, at least for reasonable chains. But it's still it seems very difficult to give a rigorous meaning to this vague statement. Right? Reasonable, you might think that because of what I just said, you might think that if you add some sparsity, if you restrict yourself to sparse chains, at least this product condition should be the right condition. But it's not. You have counterexamples even within the world of random walk on bounded degree graphs, for example. Right, so it's very delicate to make this into a precise statement. There has been attempts, and actually what is known for now is that the conjecture holds for two very nice simple classes of Markov chain. It's known to hold for burst and death chains. Right? Which is already a nice resume by Ding, Lubetsky, and Perez from 2010, I believe. And this result was more recently extended beyond burst and death chains, so beyond one-dimensional chains, to simple random walks on trees. So this is a more recent work by Vasu and Perez, which goes into this direction of the previous statement here. But still, if you think of the examples I started with, so interacting particle systems or random walk on complex networks or Markov chain Monte Carlo methods, this is very, very far from applying to those examples. Right? So I hope that you are now convinced that there is a beautiful question here and that it deserves more attention. Okay, so I'm going to stop here, and after the break, I will describe a new approach, a new progress that I recently made on this problem of understanding the cutoff from a general point of view.
Thank you very much. Are there questions so far?
I have a quick question.
Yes.
Are there any known examples of cutoff phenomena in Markov chains that have countable states?
So then, you need to define what you mean exactly, because, this phenomenon is really something that is asymptotic as the size of the state space tends to infinity. Now, if you already work on an infinite state space, there is something that should go to infinity. So we may, for example, consider that the initial condition is coming from further and further away or things like that. So you need to change the definition of a cutoff for the question to make sense, right? So this has been done. And if you define cutoff properly, then you can also ask the same question. Can you characterize the dynamics that do satisfy cutoff or don't? And the question is open exactly as in the same as in the finite case. It just makes less sense, I would say, from the point of view of concrete application. Mixing time is interesting in MC methods or for the PageRank algorithm, for example. It's not clear how meaningful it is for infinite state spaces. That's the only thing I would say.
Thanks.
Sorry, can you show once more what is the situation with cycle, with a simple random walk on cycle?
So I'll come back to this one.
Oh, yes, in the beginning, yes.
Yes.
So so psi, you normalize it. So it's not valid. There's no cutoff, no cutoff phenomenon. No cutoff.
No.
Yes.
So yes, this
No.
function psi really looks like the picture I showed just before. So this is actually the function psi from this example. Right? So it's very smooth. The convergence to equilibrium, once you rescale times by n square, that's what you see. Right? So no phase transition.
Yes. Can you show once more the formula? Yes, in the beginning. Oh, yeah. Yes. Okay. I see. FT. Yes, I see. Thank you.
So I suggest that we take a pause, maybe 10 minutes or.
Sure.
Yeah.
So we recombine at 9:10 here and whatever 10, whenever you are.
Okay.
Okay. Okay. Let's wait for Justin.
Yeah, I'm here.
Okay, if you want, when you want,
Okay.
please.
Okay. So now
Before you start, there was a question in the chat that we oversaw. Maybe are there any good examples for which we could predict cutoff phenomena without knowing details of Markov chain?
Again, the only known classes where you do have a criterion are birth and death chains and random walks on trees so far. But maybe at the end of the talk, you will have another answer to this. Okay, so let me now describe a new approach to this general understanding of the cutoff phenomenon via entropy and curvature. It's just the starting point of general direction that I think is worth trying to push further. And I hope to convince you that this is indeed the case. Okay. So let me start by describing the relation between entropy and mixing. This is very well known. So one of the main problems with estimating mixing time is that total variation distance is not at all a tractable quantity. It's very badly behaved in many, many ways. Right? It's not an analytical quantity. So a natural idea is to replace this quantity by another measure of distance, which is more analytical or more tractable. And this has been done with a lot of success over the past years. And one of the examples of a distance which is much more tractable than total variation distance is this relative entropy. Right. So let me recall the definition. So the relative entropy between a measure mu and a reference measure pi, still on my finite state space X, is defined by the following formula. We take a sum of all possible states, and then it's mu x log mu x divided by pi x. Right. So by concavity, this is always non-negative, and it's equal to 0 if mu is equal to pi. So it's just a measure of the distance between mu and pi, but it's much better behaved than the total variation distance in many respects. Okay, so before I explain that, let me point out that you can express this as an expectation. Right? It's the expectation of the log likelihood ratio, right? Where in this expectation, this random variable x has this function mu, and this function f is just the density mu over pi. Right? It's just another way to rewrite this, but it will be useful later. Okay. So this relative entropy is always an upper bound on total variation distance, right, by Pinsker inequality, but it's much more tractable. It behaves in a much better way. So to convince you of that, let me just give you one important property that this relative entropy has and that total variation distance does not. Right? It tensorizes. Right? If you look at product measures, if you want to compute the relative entropy between a product of several measures and another product of several measures, it's just the sum of the relative entropy of the margin. Right? And this is a very nice property that you can, for example, apply to the hypercube, where you have independence between coordinates, to get explicit formulas for the relative entropy to equilibrium, and this you would not have with total variation distance, right? So that's one aspect in which it's much better. There are others, okay? But so the main thing is that, you know, so this is for two measures, but of course, if you want to understand a Markov chain, right, you define or your favorite Markov chain, you may want to look at this quantity. So you replace total variation distance by distance in relative entropy. So it's defined still in the same way as before. You take a maximum of all initial states, and then you measure distance to equilibrium starting from X, but using this relative entropy distance. Now, this quantity, as I said, is a very good upper bound on total variation distance. So it provides a very tractable and very sharp often upper bound on the quantity that you are trying to estimate, which is the total variation distance. Actually, it's a bound on the square of the total variation distance, and there is a 2 in Pinsker's inequality. But really, the spirit is this, that you replace your nasty total variation distance with something which is analytical. And by analytical, I mean that, for example, this quantity can differentiate with respect to time, and you will find nice formulas. Right? So there is a whole theory of estimating this derivative, and this is known as log-Sobolev inequalities or modified log-Sobolev inequality. And it's very successful in order to obtain sharp upper bound and mixing times in many, many models. But I mean, to get those bounds, you need to find the optimal constant in those log-Sobolev or modified log-Sobolev inequalities, right? And even if you manage to get the precise optimal constant, it's still not clear that this precise optimal constant will give you an accurate bound on the total variation distance. So right, it's very unlikely that this method will allow you to prove a cutoff. Right? It's very good for estimating mixing times up to prefactors, but it's not fine enough for cutoff, usually. So that's not what we are going to do. But what we are going to do instead is to look at a second order version of relative entropy, which is somewhat new in this context, and it's called the var entropy. And it will be the key quantity for the rest of the talk. So let me define this. Okay. So take a measure mu as before and define the var entropy of it with respect to your reference measure, exactly as we did for relative entropy. So you sum over all states, then mu of x log mu x over pi x, right? Except that now you subtract the relative entropy and you square. Right? So what is this? It's just the variance of this log likelihood function that I introduced there. Right? It's just the variance associated with the expectation that defines relative entropy. Right? So relative entropy is a very well-studied and well-known quantity. This var entropy, the second-order version of it, has not been studied much. It was introduced a decade ago in the context of coding, so compression of codes, right? So it has nothing to do with Markov chains. It was introduced there because this var entropy here is the natural way to measure the error in the asymptotic equipartition property, which is fundamental for coding theory, right? But what I claim is that it's the good notion if you want to understand mixing, the cutoff phenomenon for Markov chain. So let me first say that this var entropy looks like a complicated quantity, and it is, but it has nice properties. For example, it does tensorize exactly as relative entropy. Right? Exactly the same formula as we had here is valid with D replaced by V. And the reason is simple, right? If you have a product measure, then the density here will be a product of marginals. And when you take the log, you get a sum. And because the terms are independent, the variance of the sum is just the sum of the variances. Right? So it does tensorize. It's a nice, let's say, it's a nice quantity. And now the claim that I make, so of course, if you have a Markov chain, you want to define the var entropy at time t exactly as we did before, right? They take a max over all initial states and then compute the var entropy of the distribution at time t starting from x compared to equilibrium. Right? So this is a new function of time, which has not been studied before for Markov chains. And my claim is that understanding this function is the key to understanding cutoff. Right? So I would like to convince you of that. So var entropy. Right? And this is what I'm going to make more precise in the next slide. Okay, but I like you. I want to pause for 5 seconds so that you really digest this definition of var entropy, because it will be crucial. Okay, So now let me give you a formal statement that shows that the entropy is indeed a good quantity for cutoff. It's the first result of this talk. There will be only 2 results in my talk. So the entropy criterion for cutoff is the following thing. So it's a theorem that applies to any Markov chain. There is no restriction. Right? It appeared on arXiv in 21, but it's now accepted for publication. You can find it on my webpage. The result is the following. So you take any transition matrix. Matrix K, and any epsilon. Makes sense to think of epsilon as being small, but between 0 and 1/2. And what this theorem gives you is a bound on the width of the mixing window. Right? Remember that if you want to prove a cutoff, you want to prove that the distance to equilibrium drops very quickly from close to 1 to close to 0. So what you want to understand is not really the mixing time, but the difference between the time to start mixing and the time to complete mixing, in some sense. And that's what this theorem provides. The mixing time, the time it takes to completely mix, so think of epsilon being very small, minus the time it takes to start mixing, 1 minus epsilon. This is small, and how small depends on the var entropy. So you have a universal constant, which is just 2 over epsilon. Then you get this relaxation time, which is a very well understood parameter for Markov chain. And then 1 plus square root of this var entropy, this new quantity. Var entropy computed at the mixing time. So it looks like a complicated thing, but let me give you immediately the main application of that. So in particular, cutoff occurs for any sequence of Markov chain. You have cutoff as soon as a certain condition is satisfied. Now, what is this condition, right? Cutoff tells you that the distance to equilibrium is close to a step function. So what you want to control, what you want to say is that this time interval here, this time difference, is much smaller than each of those 2 quantities. Right? That's what a cutoff is. Right? And now, if you use this estimate here, you get this criterion. Right? The mixing time of your system divided by the relaxation time of the system. And again, everything should be indexed by n, but I don't want to put indices everywhere. Right? Should be in the infinite volume limit, much larger than 1 plus square root of this var entropy term at the mixing time. I'm forgetting the epsilons, but remember that the mixing time does not depend on epsilon up to 3 factors, so we don't really care. Okay, so that's the main new condition. That's the first effective sufficient condition for cutoff. Right? So let me comment on this condition, maybe. So a few remarks. The first obvious one is that if you remove this var entropy term, the square root of VKL term, what you get is precisely the product condition. Right? So if you remove this term, it is the product condition, which is necessary but not sufficient. And what the theorem tells you is that if you correct it by adding this var entropy term, then you turn your necessary condition into a sufficient condition. Right? It really resembles the product condition, and if you want, it's a correction to this product condition, which suffices to make it a sufficient criterion. Of course, it has to be stronger, and this was expected because you know that there are counterexamples for the product condition. The second thing is that now we have a new criterion for cutoff. The question is, when does it hold? Right? Can you find examples where it holds? So let's start with our first example. Right? We see the cycle does not satisfy the product condition, so there is no cutoff. Now for the cube, you can check that this condition is satisfied. And so there is cutoff. And this is very easy to see because remember that this var entropy rises, right? It's just the sum of the individual var entropies when you have product measures. And for the hypercube, this is the case. So you can compute this quantity exactly, and you can check that this quantity is actually of order 1 for the hypercube. And therefore, you do have cutoff in that case. Right? Of course, it's not specific to the hypercube. You can do the same reasoning for any product Markov chain in the world, right? As well as any high-dimensional product of Markov chains. Right, but of course, there is nothing new here in the sense that for those examples, you have other ways to check that indeed there is a cutoff. So var entropy does not bring you something new. I'm just claiming here that it's the correct explanation behind cutoff, at least on those examples. But that's it. And also, what you can do is take a look at the papers that proves cutoff for various models of sparse random graphs. And in all those papers, if you inspect the proof carefully, you'll see that all the ingredients are there to deduce that actually this criterion is also satisfied in those cases. So you can see this as the common ingredient behind all those proofs. Say cutoff on random instances. Results.
May I just ask one short question?
Yes.
This sign means much larger, right?
Yes.
This double larger.
Yes.
Could this? Yes. Could this be improved? I mean, what exactly does it mean? Much larger? Could there be any measure how large could be the distance between the terms?
You don't need, I mean, if you want to have a cutoff, you just need that this ratio divided by this quantity tends to infinity. Right? Now, if you manage on your concrete example to have a specific quantified version of this, what you will get is a specific quantified version of the sharpness of your phase transition.
Okay, thank you.
Cutoff is about saying that this is close to a step function, and if you can estimate, if you have an estimate on how much larger this is compared to this, what you will deduce is how much smaller this is compared to this. Right? So you get a quantitative cutoff if you want.
Okay, thank you.
Okay. So now, this condition so far, it's nice. It's just nice because it gives you a general sufficient condition for cutoff. It seems to apply well, at least to some examples where you can do explicit computations. But so far, it doesn't give you any new result about cutoff, right? Because it requires estimating this quantity. Right? So my claim is that this quantity can be estimated in certain classes of chains, and that for those chains, it gives you new examples of cutoffs, and that's what I'm going to present now. Right. So if you want to understand this, to estimate this var entropy, you need to put assumption on your Markov chain. Otherwise, I do not know how to estimate it. But what I will present is a broad class of Markov chains for which this can be estimated, and those Markov chains are non-negatively curved Markov chains. Right? So that's where curvature enters the play. Okay. So let me talk about curvature. So as you probably know, curvature comes from the geometry, the Riemannian geometry of manifolds, right? It is a very powerful notion there, very classical also. And it was so powerful that people have started to try and define analogs of this notion of curvature for discrete spaces, and in particular, graphs and Markov chains. And so there are many approaches, many ways to define a discrete version of curvature. And those notions are not equivalent one to another. Right? One very simple and successful notion of curvature is the one introduced by Yann Olivier in a paper in 2009. There is also a very nice survey also by Jan Olivier 1 year later, which is very easy to read, and which explains the connection between this discrete notion and the continuous notion of curvature. So I'm going to stick to this nice version of discrete curvature, but for those of you who know other versions, for example, the Bakry-Emery curvature condition, all that I'm going to say also applies to this alternative notion of curvature. Okay, so to define this Olivier notion of curvature, I will need to make an assumption on my Markov chain, a very simple assumption, which is that the diagram of the chain should be symmetric. So I want that from now on, I will assume that whenever you can go in one jump from X to Y, you should also be able to go from Y to X. So for example, any reversible chain satisfies this. But this is much weaker. Right? It does not tell you anything about the probability of those transitions. It's just saying that if the transition is non-zero, the probability is non-zero in one direction, it should be non-zero in the other direction. And the reason I'm doing this is that then I can define a distance of my state space as follows. So the distance between two states will be just the number of jumps that you need to make in order to go from X to Y. So it's the minimum integer n, such that you can go from X to Y in n steps. And because of this assumption, this is a symmetric quantity, so it is indeed a distance. It is a distance on the state space. Right? If you think of a simple random walk on a graph, that's exactly the graph distance. Okay, and now that you have a distance on the set X, you can extend it into a distance between probability measures on that set using optimal transport. So how do you do that? You use Wasserstein distance. So take two probability measures on X, mu and nu, and define their distance as follows. So you generate a random state according to mu, then you generate a random state according to nu, and now you have two states, so you can compute their distance. This is a random quantity, but if you take expectation, you get something deterministic. Right? Still, this quantity depends not only on nu and nu, but on how you couple them together. Right? And you are free to choose any coupling that you wish so that you minimize this distance. Right? So that's the Wasserstein distance. It's a nice metric on probability measures. And one important remark is that if you look at Dirac masses, then their Wasserstein distance is just the original distance between the points. Right? So in this sense, it's really an extension of the distance. You can view this Wasserstein technology as a way to lift any distance on a set into a distance between probability measures in a way that the new distance is an extension of the previous one, right? in this sense. Right? And this does not assume anything about the distance. Here we chose to work with the specific distance between points, but you can replace this by any distance on X, and this definition will immediately give you a new distance between probability measures. So it's a very general construction. In particular, if you take as a base distance, instead of this graph distance, you just take the trivial distance, the one which is 1 when X and Y are different and 0 otherwise. And this here is precisely the total variation distance. So it's a very general construction in order to obtain metrics on probability measures. And because of what I just said, if you look at the total variation distance between two measures, mu and nu, right, you can also write it as an infimum over all possible coupling. But now you take this trivial distance, which is indicator that X is different from Y, and so what you get is this, which you probably already know. Right? But this is always smaller than this distance because this distance is integer value. Right? So you always have this inequality. Right? So this goes in the same direction as what I said before, that if you want to understand this total variation distance, a good idea is to replace it by an upper bound or a lower bound which is more tractable. And that's what this Wasserstein distance does. Right? It's something that is always an upper bound on total variation, but somehow is more tractable because it takes into information distances between points in a much more relevant way. Okay, and now you can hope that for your Markov chain, you will be able to understand how this evolves in time in order to get bounds on total variation distance. And that's precisely what Olivier did. So he defined the curvature of the chain to be the following. So the curvature of my chain K is defined as the largest number C, such that anytime you apply the transition matrix K, the Wasserstein distance decreases by the factor C. Okay? So you have Wasserstein distance between K applied to mu and K applied to mu would be at most 1 minus C times the original Wasserstein distance. And this should be true for all measures. So you are really, you want to have a contraction in this Wasserstein distance whenever you apply the transition matrix K, because this will give you a way to keep track of the evolution of this distance in time along your Markov chain, and therefore get good bounds on this separation distance. Okay. Let me just emphasize that I'm talking about contraction here, but be careful that this is not necessarily less than 1. So this C here needs not be positive, could be negative. So when you use total variation distance and you apply the transition matrix K, the total variation distance can only decrease. It's a nice quantity which is always reduced under the action of a stochastic matrix. When you move to Wasserstein distances, this is no longer true. So it could be very well be the case that this quantity here is larger than this level. So that's why I need to allow values of C that are negative. Of course, this inequality will be interesting only when C is positive, right? So that you really have a contraction. So chains with a curvature which is positive, strictly positive, or at least non-negative, right, are extremely nice. They are very nice property, right, in terms of mixing times, but also in terms of geometry and concentration of measures. So this is a well-developed theory that is very interesting. Yeah, I'll mention examples of chains which have non-negative curvature in the next slide. But what I would like to do now is make a very important comment. It's a very simple claim, but it's fundamental, I think, for this notion of curvature. Right? This property here seems very delicate to check in practice, right? Because it's a global quantity. You want some sort of contraction between any two measures, mu and nu, in your state space. But in fact, and this is one of the main reasons why this curvature is so successful, in fact, you only need to check this inequality for a very specific subset of measures, namely enough to check this. So this condition here, when mu is just a Dirac mass, nu is another Dirac mass, and the points x and y are neighbors. So the distance between them is there. If you manage to, yes?
There is a question. Is it possible to always choose the distance so that the curvature is non-negative?
Yes, it is. For example, take total variation distance, and then you always have contraction in this. The curvature will not be strictly positive, but at least it's non-negative. Okay, so if you want to check this geometric condition here, all you need to do is to check it for a very simple special case of measure, and it's enough by the triangle inequality and some sort of convexity of this Wasserstein distance. It's enough to check this. And so what do we have to do in practice in order to prove that a chain has a certain curvature? You just need to pick two neighbors in your state space, x and y, and you need to simulate one transition starting from x and one transition starting from y. Right? You need to couple those states so that the distance between them on average is as small as possible. And if you can prove that on expectation, this distance can be made less than the original one, which was, the distance here was 1, can prove that on average, the distance that you end up with in the end is smaller than 1, then you do have positive curvature. So that's what we need to do. So this is a very nice property because it really reduces this claim to something that is local and easy to check in practice. And I'm going to use that now to give you a lot of examples of chains which do satisfy this non-negative curvature property. So let me give you examples. Chains. If you want to have good mixing time bonds, then you really want the curvature to be strictly positive and to have some quantitative control on that. But here I'm only requiring that the curvature is just non-negative. And so I'll give you examples of chain with non-negative curvature. Right, so let's start with the simple setup of simple random walk on graph because it's very intuitive. So if you take simple random walk on, say, the complete graph, then it's very easy to find a coupling such that the distance decreases. Also for paths, for cycles, for stars, for cubes. Right. All of that, it's very easy to do by hand, to construct by hand a coupling that will have the property that the distance in expectation can only decrease under the Markov chain. And so therefore you have non-negative curvature. Okay. Let me give you a much larger class of chains which do have non-negative curvature. So those are simple random on any abelian Cayley graph. In particular, the two examples I gave you before, but way more general than any abelian Cayley graph. So why is that? Right. So remember that what you need to do is to pick a point in your a vertex in your Cayley graph, a neighbor of it. Right? So those are at distance 1. And then you need to simulate one step starting from x and one step starting from y in a joint way so that the expected distance is atmosphere. How do you do that? Well, if you are doing a simple random walk on an abelian Cayley graph, then doing one step of your Markov chain is just adding to x a random generator, a random element from your set S. And the obvious way to couple those two random points is just to take the same random generator for both trajectories. Now, if you do that, and if your group is abelian, then those two points here will also be at distance 1, just because the diagram is commutes, right? And therefore, you have a coupling that preserves the distance, and so you have non-negative curvature, right? For any random walk on an abelian group. Okay. Actually, it's more general than that. You don't really need the group to be abelian for this argument here to work. The only thing that you need is that your Cayley graph has the following property, right? The set S should be conjugacy invariant. What does this mean? Simply means that take any element of your group, multiply on the left by x, and then on the right by x inverse, and you should get S back. For all x in the group. Of course, this property is trivial if your graph is abelian, because then you can just move this one on the other side. But here is an example of a non-abelian Cayley graph, which does satisfy this. It's a famous graph. You just take X to be a set of all permutations, so the symmetric group on n elements. And then your generating set is just the set of transpositions. Transpositions are invariant under conjugacy, so what you get in the end is a graph that satisfies this property, and therefore this coupling shows that you have non-negative curvature. Okay, it's a very important graph, and the simple random walk on this graph has been studied by many people. Okay, let's go a bit beyond simple random walks on groups, on graphs and groups. Let me move to, say, interacting particle systems. So if you know about this simple symmetric exclusion process on a segment, it's pretty easy to find a coupling that will show that the curvature is non-negative. Right? And you can think of simple symmetric exclusion as a corner flip dynamic. Right? You have paths that goes up and down, that start at 0 and end up at 0. And what you need to do, right? And oops. Okay. Sorry about that. Yes, so in this corner flip dynamics, what the Markov chain does is that at any step, you pick one of the position here and you try to move this up or down with a certain probability. Right? And all those dynamics have a certain monotone property which guarantees that you have non-negative curvature. Okay, another nice interacting particle system that has non-negative curvature is the mean field zero range process with increasing rates, with monotone rates. And again, it's a very well-known property. And finally, if you care about Gibbs sampling, so Glauber dynamics, if you prefer, take your favorite spin glass model and just look at Glauber dynamics for this spin glass model. And if your temperature is high enough, then you will have non-negative curvature. That's again a very classical and easy result. But if the temperature is high enough, you will find a coupling that is contracted in this sense here, and so you have no negative curvature. Right? So I hope to convince you that this curvature assumption is not a big thing. I mean, it's something that is satisfied by many Markov chains. Maybe let me give you a counter example. So an example that is not that does not have non-negative curvature. Right? Think of simple random walk on a tree, for example. Right? If you have a tree, right? Here is X, here is Y, here is Y, and then you have many neighbors here going outside. Then, of course, if you try to couple one step starting from X and one step starting from Y, right? They will have a drift towards the exterior, and so the expected distance will increase on average. Right? So you cannot have non-negative curvature. And also, similar idea, but more difficult to prove, simple random walk on any expander will have negative curvature. So you don't have this nice contraction property. Okay, and now, why is it good to have non-negative curvature? So let me give you the second main result of the talk. And the main result is saying that, if you have non-negative curvature, then there is a universal estimate on the var entropy, right, that does not require anything complicated about your Markov chain. Right? So here is the precise statement. So if K has non-negative curvature, then you can estimate the var entropy as follows. So the var entropy at any time grows linearly with time, at most. Right? So there is a universal constant, and then time. And then there is something here that depends on the Markov chain, but in a very simple way. It's just log square of P, where P is a sparsity parameter. P is just the minimum non-zero entry of your transition matrix. P is the minimum of KXY for points that are neighbors in your Markov chain. Right? So if you think of simple random walk on a graph, then P is just 1 over the degree. Okay, so you have this very general estimate on var entropy that does not depend at all on the specific details of the Markov chain. And remember, that, so this is theorem B. Remember that we had a theorem A, which tells you that if any Markov chain has a small var entropy, then it has cutoff. So when you combine those two, you get an effective criterion for cutoff. So corollary. And again, it's just putting A and B together. So so non-negative, so chains with non-negative curvature exhibit cutoff. Cutoff if, and here is the criterion, so you just plug this estimate in theorem A, and what you get is the following when you simplify. You just want the mixing time of your chain to be large compared to the relaxation time squared times log of P. So that's a very simple to check, a very simple condition to check that guarantees that you have cutoff, but it's restricted to chains that have non-negative curvature. So, for example, all the chains that I listed in the previous slide. Okay. So let me give you an example so that you see more concretely what this means. Consider a simple random walk on an abelian graph. Again, this is a Markov chain that always has non-negative curvature. Exhibit cutoff. Now, if you write this condition, then P will just be the degree in my graph, 1 over the degree. But you still have to estimate the mixing time, and you may argue that this is difficult. Right? So what I can do is always say that my mixing time is at least, this is a very rough upper bound, log of the number of states divided by log of the degree. That's a very rough lower bound on the mixing time. It's just saying that, you know, in order to mix, you need to see a decent proportion of your state space. And in order to do that, you need to do at least this many number of steps. So when you plug this estimate in this criterion, what you get is that there is cutoff as soon as the relaxation time is small, and small just means log n over log d cube.
Sorry, what are N and G? What are N and G?
Yes, so that's what I'm going to say. So this is the number of vertices, and this is the degree. The number of neighbors of every vertex in my graph. Right. So if you give me any abelian Cayley graph, right, the number of vertices is something very simple, the degree is something very simple, and if I know both of them, then just a rough estimate on the spectral gap of my graph will guarantee cutoff. Right? So it's a very effective criterion for cutoff. So to conclude, I would like to just present an application of that to a very sexy problem, in my opinion. So it was a conjecture by Aldous and Diaconis. So let me speak a bit about that. So its application to random Cayley graphs. So Cayley graphs are very important in many branches of mathematics, and it makes sense to, if you want to understand their typical structure, it makes sense to look at Cayley graphs that are generated at random. So how do you do that? Well, you fix your favorite group. Upside n. Right? And then you choose a generating set as follows. You choose S including X uniformly at random among all sets with a given cardinality, which I'm going to call D because then it will be the degree of my. Now, you may think of the size of the group as being very large, so tending to infinity. And if you want your graph to be connected, you should choose D large enough, right? Otherwise, you don't have enough generator to connect the graph. Right? And the correct threshold here is, if you think of the hypercube, for example, you need to have slightly more than log n degree slightly more than log n. And it turns out that if you do this, then with high probability, your graph, the random graph that you obtain, will be connected. So look at the random graph, which is the Cayley graph on X generated by this random set S. It will be connected with high probability. It's very easy to see. And so you can ask, how long does it take for the random mode to mix, and will you have cutoff? Right. But actually, this was a question that was asked by Aldous and Diaconis. It was actually conjectured that there is cutoff. In one of their papers from the 90s, I believe. And this problem has attracted quite some attention. There is a very nice work by Du and Hildebrandt, who managed to get partial progress. I will explain what exactly. I think it's 98. What they did is study the case where the degree is very large, so much larger than, again, much larger than what you need to actually get a connected graph. Right? And in this regime, things behave nicely. And so you can prove that indeed the simple random walk in this regime exhibits cutoff. And finally, the problem was solved by Jonathan Herman, very recently, and Sam Olesker-Taylor. In a remarkable series of work, which is very impressive, and they managed to tackle the regime where the degree is log n, which is the hard regime where the graph is barely connected, if you wish. Right? And they do this by a very model-specific detailed analysis of the geometry of those random Cayley graphs. Right? So it's very nice, right? But still it's model-specific. And what we obtain here with our criterion, the criterion that I presented just before, is that we recover this result just for free, right? Effortlessly, without having to do any specific computation. Right? Let me just point out that in the criterion I just gave, you need a rough estimate on the spectral gap. And this estimate is provided here by a very classical result of Alon and Reuschmann, which tells you that in the regime we are considering, the relaxation time is actually of order 1. It's actually constant. By a result of Alon and Reuschmann. Very classical result from 19,000. Right, so if you plug this constant relaxation time estimate in the previous here, this is constant, but this is diverging because the degree is logarithmic in n, and so you do have cutoff. And of course, this proof is not at all model specific in the sense that it applies to any Cayley graph that satisfies this assumption here, and not just this specific random model that was studied by Herman and Olesker-Taylor. Okay, so I'm going to stop here. The only thing I wanted to mention is that now I hope you are convinced that at least the cutoff phenomenon is an interesting phase transition to understand, and that maybe var entropy is an important quantity to estimate, understand if you want to understand cutoff. Right. What I did here is just provide a general estimate of this var entropy for a certain class of chains, so chain with non-negative curvature. But you could try to estimate var entropy for your favorite model of Markov chains, maybe the examples that I gave at the beginning, and maybe hope to get an understanding of the cutoff phenomenon there. So that's essentially what I'm going to try and do in the coming years. But if any one of you is interested, I'll definitely need help. So you're welcome.
Thank you very much. This was extremely nice. Is there questions? There is one in the chat. Could you say a few words about the relation between sparsity and curvature?
Sure. So one important thing about one important conjecture in this setup is that random walk on any Cayley graph which is an expander should satisfy cutoff. It's a very famous conjecture, right? And of course, here if you have an expander, then the relaxation time is order 1, so you are happy. The degree is fixed, and this n is diverging, so it seems that you do have cutoff. Right? The only problem is that you have this assumption that your chain has non-negative curvature, right? And it turns out that it's not possible for a chain to be an expander if it has non-negative curvature. So the problem comes from the sparsity. Right? If you want to have non-negative curvature, n sparsity, then this implies that the relaxation time has to be non-constant. So that's they do not go well together, sparsity and curvature in some sense.
Another question in the chat. Do you know if the historical example rifle shuffle has a positive curvature?
That's a good question. I've never thought about this, so I should try to pick the top link to check. Yeah, that's a good question.
Are there other questions in the audience? Yeah,
I have a
Steven?
quick question. So can you tell a little bit about what goes on behind theorem B, that how you translate the notion of non-negative curvature into a bound on Entropy?
Sure. So this is actually, the proof is very simple. I mean, very simple. There are 2 steps, and it's very easy to understand those 2 steps. So remember that the entropy is essentially a variance. You want to understand the variance of log of ft of xt, where this is the position of your random walk at time t, and this is the density with respect to the equilibrium measure. You want to understand this point. Now, you use curvature to say the following. Right, so if K has non-negative curvature, then you get concentration estimates for any function. Okay? You can compute the variance of any, starting from any initial condition, the variance of any function of your Markov chain at any time, and you get this nice estimate that it grows at most linearly with time, and the constant here depends on h, and it's just the Lipschitz constant of h, right? So how much h varies when you do one step of your Markov chain, right? So this is a very well-known and very general estimate. And what I did is just apply this estimate to the specific case where h is log of ft. Now, this is a bit of a delicate function, right? It's the log of the probability to be at site y when you start from x divided by the stationary mass of y. That's h of 1. And what you want to understand is how this quantity, what's the Lipschitz constant of this quantity? And the claim is that this specific Markov chain here, this specific function h has a Lipschitz norm, which is up to a universal prefactor, roughly log of the sparsity parameter, right? And when you combine those 2 things together, you do get exactly the estimate I gave, right? So the only difficulty is in having a Lipschitz estimate for the log of the heat kernel. So you need gradient estimate, if you wish, for the log of the heat kernel, which in discrete time has not been done a lot. So yeah, that's the way.
Is there an intuition behind the first inequality? So essentially this contraction is giving this linear bound on the variance. So is there an intuition for that?
Yes, so I can even prove that it's one line. So there is a formula for the variance in general. The variance, you can write it as an integral. So the variance is just pt of f squared minus pt of f squared, evaluated at the initial point x. But this, you can always write it. There is a nice formula for it, which is the following. So you take, you applied your carré du champ operator gamma to PSF, and then you apply P T minus F to that, and ds. Now, if you want to bound this variance here, you just need to bound this thing. And what you use is the fact that your carré du champ operator, right, is defined as follows. So it's sum over all y, k, x, y, and then you do the difference square. And what I'm using is just the fact that this is at most the Lipschitz constant of f, right? That's the first thing. And the second thing is that this non-negative curvature tells you that the Lipschitz, so then you get the Lipschitz constant of PSF, but non-negative curvature implies that the Lipschitz constant can only decrease. So that's it. Then you get a proof of the first inequality.
Thanks.
Is there another question? Yeah, please.
Just one short question. Related to the distance that you use, relative entropy and total variation distance, those are, I think, quite common known distances. What would happen if you would analyze this in different topologies, say Skorokhod or Gromov, where you would have different distances? Would this be possible? And could this make any sense for different types of processes with cutoffs?
Okay, that's a good question. So for cutoff, I'm not sure, but definitely, for example, if you think of simple random walk on the cycle, then you can say that this model converges as a natural scaling limit, which is Brownian motion on the cycle.
Yes.
Right. So there is one folklore conjecture that tells you that whenever you do have a scaling limit like that, a well-defined scaling limit, then you should not have any cutoff because you see something that is very gradual in the limit. So in terms of what distance, other distances, so there are a couple of other distances that have been studied with respect to cutoff, and those are more analytical distances like the Hilbert norm. Right? You can look at the density, and look at the probability to be at y starting from x, divided by pi of y. Subtract 1 because this is the what you would have at equilibrium, and then you take the square of it and take the norm in your Hilbert space. Now this quantity is a certain distance, which is very analytical, very Hilbertian, if you want. And for this, cutoff is very well understood. It's actually equivalent to the product condition that I showed before. Right? But it's just that from a statistical point of view, from the original motivation of you use Markov chains to simulate things, total variation distance is really the most meaningful one, I would say.
Would those distances, the relative entropy and var entropy, also be translated to different topologies? Just like Skorokhod, say, or
I'm not sure to see what you mean.
Okay, thank you. Thanks.
There is one more question in the chat. How sharp do you expect the bound in theorem 1 to be?
That's a good question. So I think it essentially captures the right phenomenon. Okay, I don't know I don't have any proof that this is actually an if and only if, but it's very close to the product condition. Right? It's just a small correction to it, and the product condition, we know it's necessary. Right? So that's one ingredient. The second argument that I have is that it's satisfied in all the examples where we know that there is cutoff, and we can do explicit computation of this var entropy. So this gives you a good sign that it should be sharp. But even if there are counterexamples that were found to it, still I believe that it would apply to all those high-dimensional expander models that we have in mind, and so it will still explain the cutoff for a very broad class of Markov chains. I mean, but this, again, this requires that we are able to estimate var entropy for those chains, and it's not here that we can actually, but. I believe that if we can manage to estimate var entropy, then this criterion will prove cutoff for many chains. That's my guess.
Thank you. There's a question by Sam now.
Yeah, just how important is it that you use the graph distance for the curvature? So this is what I was trying to hint at earlier, that could you choose a different distance and get non-negativity of curvature, and then could you still deduce similar results?
So yes, but you see, so it's all in this slide here. Where you use curvature is to have the decrease of this Lipschitz norm. Now this will remain true whatever distance you choose, but now what is not true anymore is this first step here, where you say whenever I make a transition, my function f changes by at most the Lipschitz constant, right? This works if your Lipschitz constant is the one that I defined in my code. If you change the distance, then here this you will have to see what it gives, right? The distance should be will be distorted. I mean, you will have
Yes.
here, and you will need to see if this, I mean, if the gain that you have by changing your metric is compensates the loss that you will have.
Yes, and I guess if you pick sort of optimal distance, this is going to be pretty hard to estimate what's going to go on in this bit that you've just highlighted. So try to get a sort of yeah, okay. Thanks.
Well, thank you very much for this really exciting couple of talks. I think we all enjoyed a lot. Yeah, see you next time.
Thank you again for the invitation.
Thank you, Justin, for the talk.
Bye, guys.
Bye-bye.